Over the next couple of lectures, we will study Shannon's second theorem, which is the most important result in our study in information theory and coding. Without getting lost into the rigorous mathematical proof for the same, we will try to appreciate the importance of this theorem in the framework of a binary symmetric channel. In all modes of communication, the communication is not error free. We may be able to improve the accuracy in the transmission of digital signals by reducing the error probability. But it appears that as long as a channel noise exists, the communication cannot be error free. For example, it can be shown that in all digital communication system, the error probability, that is Pe, varies as exponential minus a constant k times Eb, where Eb is the energy per bit. By increasing Eb, we can reduce the probability of error to any desired level. Now, the signal power, which is indicated by S, is equal to Eb times Rb, where Rb is the bit rate. Hence, increasing Eb means either increasing the signal power S for a given bit rate or decreasing the bit rate Rb for a given signal power S, or both. Now, because of physical limitations on signal power S, it cannot be increased beyond a certain limit. Hence, to reduce Pe further, we must reduce Rb. What this implies, that to reduce Pe, we have to make Rb tend to 0. Thus, the price to be paid for reducing Pe is a reduction in the transmission rate Rb. So, Pe tends to 0 only if Rb tends to 0. Hence, it appears that in the presence of channel noise, it is impossible to achieve error-free communication. Thus thought communication engineers until the publications of Shannon's classical paper in 1948. Shannon published his classical paper titled Mathematical Theory of Communication in Bell System Technical Journal in two parts in July 1948 and October 1948. The gist of Shannon's paper is that the presence of random disturbances in a channel does not by itself set any limit on transmission accuracy, but instead it sets a limit on the information rate for which arbitrarily small error probability can be achieved. We have studied that messages of source S with entropy given by Hs can be coded by using an average of Hs binary digits per message. This encoding has 0 redundancy. Hence, if we were to transmit this encoded message over a noisy channel, some of the information will be received in error. There is absolutely no possibility of error-free communication over a noisy channel when messages are coded with 0 redundancy. The use of redundancy in general help to combat noise. This can be seen from a simple example of a single parity check code. In this coding scheme, an extra binary digit is added to each code word to ensure that the number of ones in the resulting code words are always either even or odd. Now, if a single error occurs in the received code word, then the parity is violated and the receiver requests for retransmission. This is a rather simple example to demonstrate the utility of redundancy. More complex coding procedures can be adopted to correct n digits error, and these are discussed in the literature. Now, the addition of an extra digit increases average word length to HS plus 1, giving the code efficiency eta equal to HS divided by HS plus 1, because code efficiency is defined as the entropy of the source divided by the average length of the code, and the redundancy in this case is 1 minus eta, which is equal to 1 by HS plus 1. Thus, the addition of an extra check digit increases redundancy, but it also helps combat noise. So, immunity against channel noise can be increased by increasing the redundancy. Shannon has shown that it is possible to achieve error-free communication by adding sufficient redundancy. For example, if we have a binary symmetric channel with an error probability PE, then for error-free communication over this channel, messages from a source with entropy HS must be coded by binary codes with a word length of at least HS divided by CS, where CS is the channel capacity for a single usage of a binary symmetric channel, and which is equal to 1 minus PE log 1 by PE plus 1 minus PE log 1 by 1 minus PE. Now, the efficiency of this code can never be greater than CS. So, if a certain binary channel has CS equal to 0.4, what it implies that a code that can achieve error-free communication must have at least 2.5 times HS binary digits per message, which is 2 and 1.5 times as many digits as required for coding without redundancy. This means that there are 1.5 times HS redundant digits per message. Thus, on the average, for every 2.5 binary digits transmitted, 1.5 digits are redundant or check digits, giving a redundancy of 1 minus CS equal to 0.6. As discussed in the beginning of this lecture, PE, the error probability of binary signaling, varies as exponential minus k times EB, and hence to make PE tend to 0, either the signal power should tend to infinity or RB should tend to 0. Now, because signal power must be finite, PE tends to 0 only if RB tends to 0. But Shannon's results show that for a given channel, as long as the rate of information digits per second to be transmitted is maintained below a certain limit, this limit is known as channel capacity, then it is possible to achieve error-free communication. What it means is that to attain probability of E tending to 0, it is not necessary to make RB tend to 0. So, such a goal of probability tending to 0 can be attained by maintaining the rate of information less than C, where C is the channel capacity defined per second. We will derive this relation later on, where C is equal to twice the bandwidth of the channel multiplied by CS, where CS is the channel capacity per single usage of the channel. So, the question is, where is the discrepancy? To answer this question, let us investigate carefully the role of redundancy in error-free communication. Although we will restrict our discussion here to a binary scheme, this discussion is quite general and can be extended to an Emery case. So, consider first the use of a binary symmetric channel to transmit reliable messages as shown in this figure. The input to this channel is alphabet A consisting of letters 0 and 1. The output of this channel is alphabet B consisting again of letters 0 and 1. To be even more specific, we assume that the probability of error of this binary symmetric channel denoted by P is equal to 0.01, which means that 99% of the bits transmitted are received correctly. Now, for many modern data transmission systems, this level of reliability is far from adequate. Probability of error requirements of 10 raised to minus 6, 10 raised to minus 8 or even lower are often necessary. In order to increase the reliability of our channel, we may have to repeat our messages 0 and 1 several times. For example, suppose we decide to send each message 0 or 1 3 times. So, one method of viewing this procedure is illustrated in the figure shown here. The output of this channel under these circumstances is an element of a third extension of a binary symmetric channel. So, the output is a binary sequence of length 3. We have used 0 0 0 and 1 1 1 sequences as message sequences. The probability that no error occurs in the transmission of our 3 digits is 1 minus p cube is equal to p bar cube, where p bar is by definition 1 minus p. Now, the probability of just one error is given by 3p p bar squared. The probability of 2 errors is 3p squared p bar, and finally, the probability that all 3 bits are in error will be given by p cube. Now, whenever p is less than half, that is when the probability that a bit is received correctly is greater than the probability that it is received incorrectly, then in this case it seems reasonable to decide that a message 0 0 or 1 1 was transmitted according to the majority vote of the 3 received bits. Now, it is easy to show that this decision rule is in fact the maximum likelihood decision rule. We will prove this later in this class. In any event, such a decision rule leads to a probability of interpreting the message in error given by Pe equal to the sum of the probability of 3 bit errors, that is p cube, plus 2 bit errors, that is 3 p squared p bar. Now, for p equal to 0.01, this yields Pe equal to approximately 3 multiplied by 10 raised to minus 4. Thus, we have been able to reduce the probability of error from the value of 10 raised to minus 2 to 10 raised to minus 4. Having gone this far, it is not difficult to see how to increase the reliability even further. We may send 5 bits over the channel for each binary message we wish to transmit. This is represented in the figure as shown here. We use messages 0 0 0 0 0 to transmit 0 and the sequence 1 1 1 1 1 to transmit 1. Now, the probability of 0, 1, 2, 3, 4 or 5 Binet errors in transmissions is as follows. So, for the probability of 0 error is p bar phi and the probability of phi Binet error is p phi. If we again use a majority rule, that is maximum likelihood decision rule, to decide whether 0 0 0 0 0 or 1 1 1 1 1 was transmitted, we obtain a probability of error P e equal to P 5 plus 5 times P 4 P bar plus 10 P cube P bar square. That is the sum of the probabilities of 5, 4 or 3 Binet errors. Now, again for p equal to 10 raised to minus 2, this probability of error P e is approximately equal to 10 raised to minus 5. Now, there is of course no limit to this crude method of increasing reliability. In the table shown here, we give the probability of message error when 1, 3, 5, 7, 9, 11 Binets per message are used in a binary symmetric channel with single Binet probability of error of p equal to 10 raised to minus 2. The improvement displayed in this table is not achieved without penalty. The price we pay for increased message reliability is increased redundancy in the transmitted Binets. In other words, although we may decrease the probability of error from 10 raised to minus 2 to 5 multiplied by 10 raised to minus 10 by going from 1 Binet per binary message to 11 Binets per binary message, we also decrease the message rate from 1 message per Binet to 1 by 11 message per Binet. In general, the simple repetitive method we have described can lead to an exchange of message rate for message reliability. Typically, such an exchange will appear as plotted in the figure shown here. So, the probability of message error decreases with the decrease. So, the probability of message error decreases with the decrease in the message rate. In any case, repetitions cause redundancy, but also improve the probability of error. Now, it will be instructive to understand this situation from a graphic point of view. Consider case of 3 repetitions. We can show all 8 possible sequence of 3 binary digits graphically as the vertices of a cube as shown here. This is a 3-dimensional cube in Hamming sphere. This is a 3-dimensional cube in Hamming space. It is convenient to map binary sequences as shown in this figure and to talk in terms of what is called the Hamming distance. Hamming distance between any 2 binary sequences of the same length alpha I and beta j is defined as the number of places in which alpha I and beta j differ. For example, if alpha I is equal to 101, 111 and beta j is equal to this sequence, then Hamming distance denoted by d between alpha I and beta j is equal to 3, because alpha and beta j differ in 3 places. So, in the case of 3 repetitions, we transmit binary 1 by 111 and binary 0 by 000. The Hamming distance between these 2 sequences is 3. Observe that of the 8 possible vertices, we are occupying only 2 vertices 0, 0, 0 and 1, 1, 1 for transmitted messages. At the receiver, however, because of channel noise, we are liable to receive any one of the 8 possible sequences. Now, the majority decision loss rule can be interpreted as a rule that decides in the favor of that message 0, 0, 0 or 1, 1, 1, which is at the closest Hamming distance from the received sequence. Let us provide a simple proof for the same. We have studied that maximum likelihood decision rule minimizes the error probability when all possible inputs are equiprobable. Now, this rule has a simple interpretation in terms of Hamming distance. Let us assume that alpha I is the transmitted code word and beta j is any possible output sequence. Obviously, alpha I and beta j are of the same length n. We denote the Hamming distance between alpha I and beta j as dij. Then alpha I and beta j differ in exactly dij places, and the probability that beta j will be received if alpha I is sent is just the probability that the errors will occur in the dij places where they differ, and that no errors will occur in the n minus dij remaining places. So, probability of bj given alpha I is equal to probability p raised to dij multiplied by p bar raised to n minus dij. For p less than half, the only case of any interest, probability of beta j given alpha I decreases with increasing dij. The further beta j is from the transmitted binary sequence, the less likely it is to be received. The maximum likelihood decision rule selects that code word which maximizes probability of beta j given alpha I. Hence, for any received sequence beta j, the maximum likelihood rule selects the code word closest to beta j in the Hamming distance sense. Now, this maximum likelihood decision rule can be summarized in the figure shown here. Beta j is the received sequence and alphas are the transmitted sequence. So, in this figure, beta j is closest to the code word alpha star, where the distance is indicated by small d, which is the smallest distance compared to all dij's. So, returning back to the case under discussion for 3 repetitions, sequences 0 0 0, 0 0 1, 0 1 0 and 1 0 0 are all within 1 unit of Hamming distance from 0 0 0, but are at least 2 units away from triple 1. Similarly, when any of the sequences 1 1 0, triple 1, 0 1 1 or 1 0 1 is received, the decision is binary 1. We can now see why the error probability is reduced in this scheme. Of the possible 8 vertices, we have used only 2 vertices for the messages, and these are separated by 3 Hamming units. Now, if we draw a Hamming sphere of unit radius around each of these 2 vertices, the 2 Hamming spheres are non-overlapping. Now, the channel noise can cause a distance between the received sequence and the transmitted sequence, and as long as the distance is equal to or less than 1 unit, we can still detect the message without error. Now, in a similar way, the case of phi repetitions can be represented by a hypercube of phi dimensions. The transmitted sequences in this case are phi zeros and phi ones, and this occupy two vertices of the hypercube in phi dimensions, and these are separated by phi units. Now, if we draw the Hamming sphere of 2 unit radius around each of these two vertices, then this Hamming spheres would be non-overlapping. In this case, even if channel noise causes 2 errors, we can still detect the messages correctly. Hence, the reason for the reduction in error probability is that we have not used all the vertices for messages. Had we occupied all the available vertices for messages, as is the case without redundancy or repetition, then if a channel noise caused an error, even if it was a single error, then the received sequence would occupy a vertex assigned to other transmitted sequence, and we are certain to make a wrong decision. Precisely because we have left the neighboring vertices of the transmitted sequences unoccupied, we are able to detect the sequences correctly despite channel errors within a certain limit. The smaller the fraction of vertices used, the smaller the error probability. It should also be remembered that redundancy or repetition is what makes possible to have unoccupied vertices. Now, if we continue to increase n, then that is the number of repetition, the probability of error will reduce, but this will also reduce the bit rate, that is RB, by the same factor n. But no matter how large we make n, the error probability Pe never becomes 0. The trouble with this scheme is that it is inefficient because we are adding a redundant or check digits to each information digit. To give an analogy, redundant or check digit are like guards protecting the information digit. Now, to hire guards for each information digit is somewhat similar to a case of families living on a certain street hit by several burglaries. Each family panics and hires a guard. This is obviously an inexpensive and inefficient way of doing things. A better solution would be for all the families on the same street to hire a single guard. A single guard can check all the houses on the street as long as the street is not sufficiently long. If the street is sufficiently long, then we can hire more than one guard. In using repetitions, we had a similar analogy. Repetition or repeated digits are used to check only one information digit. Using the clue from the preceding analogy, it might be more efficient to use redundant digits for a block of information digits. This is the key to our problem. Let us consider a group of information digits over a certain interval of time of t seconds, and let us add redundant digits to check on all these digits. If we continue to increase n, that is the number of repetitions, we will reduce the error probability, that is Pe, but we will also reduce the bit rate, that is Rb, by the same factor n. So, if n denotes the number of repetitions, and if we increase this, the error probability will reduce, but this will also reduce the bit rate by the same factor n. But no matter how large we make n, the error probability never becomes 0. The trouble with this scheme is that it is inefficient because we are adding redundant or check digits for each information digit. To give an analogy, redundant or check digits are like guards protecting information digits. To hire guards for information digits is somewhat similar to a case of families living on a street which is hit by several burglaries. Each family panics and hires a guard. This is obviously expensive and inefficient. A better solution would be for all the families on the street to hire one guard and share the expenses. One guard can check on all the houses on the street, assuming that the street is not too long. If the street is too long, it might be necessary to hire more than one guard. But it is certainly not necessary to hire one guard per house. In using repetitions, we had a similar situation. Redundant or repeated digits were used to check on only one information digit. Using the clue from the preceding analogy, it might be more efficient if we use redundant digits not to check or guard any one information digit, but a block of information digits. Herein lies the key to our problem. Let us consider a group of information digits over certain time interval of t seconds, and let us add some redundant digits to check on all these information digits. Suppose we need to transmit alpha binary information digits per second, then over a period of t seconds we have a block of alpha t binary information digits. If this block of information digits we add beta minus alpha times t check digits, that means beta minus alpha check digits or redundant digits are added per second, then we need to transmit beta t, where beta is greater than alpha digits for every alpha t information digits. Therefore, over t second interval, we have alpha times t information digits beta times t total transmitted digits where beta is greater than alpha, and this implies beta minus alpha times t are check digits or redundant digits or guard digits. Thus, instead of transmitting one binary digit every 1 by alpha seconds, we let alpha times t digits accumulate over t seconds. Now, consider this as a message to be transmitted. Therefore, there are total of 2 raised to alpha t such super messages Thus, every t seconds we need to transmit one of the 2 raised to alpha t possible super messages. These super messages are transmitted by a sequence of beta times t binary digits. What this implies that there are in all 2 raised to alpha times beta t possible sequences of beta times t binary digits. And this can be represented as vertices of a beta times t dimensional hypercube. Now, because we have only 2 raised to alpha times t messages to be transmitted, whereas 2 raised to beta times t vertices are available, we occupy only a 2 raised to minus beta minus alpha times t fraction of the vertices of the beta times t dimensional hypercube. observe that we have reduced the transmission rate by a factor of alpha by beta, and this rate reduction alpha by beta is independent of t. The fraction of the vertices occupied, it is also known as occupancy factor, by the transmitted message is 2 raised to minus beta minus alpha t, and this can be made as small as possible simply by increasing t. In the limit, as t tends to infinity, the occupancy factor approaches 0. This will make the error probability go to 0, and we have the possibility of error-free communication. One important question, however, remains to be answered. What must be the rate reduction factor, that is alpha by beta, for this dream to come true? We will try to seek an answer to this question in the next class, and we will also look into the verification of error-free communication over a binary symmetric channel.